Hello there. Welcome to Fundamentals of Biology, Lesson 1, The Ingredients of Life. So today we're going to start by taking a look at elements and atoms. Then we're going to take a little bit of a closer look at those atoms by looking at the atomic structure. And then we're going to talk about how we get from basic atoms up to the complexity of life that we see around us. Because quite clearly, when you look around you at the world, what you're not seeing is just a soup of individual atoms. They come together to form compounds and molecules, and those compounds and molecules form the basis of life and of nature and of inanimate objects that we see around us. So from these really humble beginnings of the basic atom, we get great complexity and diversity in the universe. So we're going to start our journey today by talking about these things. Okay, so let's start off by asking the question then, what is matter? Not what is the matter, that's a very different question altogether, but what is matter? Well, matter is basically anything in the universe that has mass and volume. So anything that sort of takes up space and has mass to it. So stuff, essentially. So it can be the air around us, it can be solid rock, it can be human tissue. It's all made up of matter. And all matter is made up of elements. So what are elements then that make up this matter? Well, an element is a substance that cannot be broken down to other substances by chemical reactions. So they're basically the smallest or the lowest level that you can get to while still being that particular element. And as far as we know, there are 92 naturally occurring elements. It could be said that we could find additional naturally occurring elements in other parts of the universe, but obviously we're not quite out there and at that level yet where we can find them. So all scientists are able to go by or go on is what we can actually see around us. And at the moment, we know that there are 92 naturally occurring elements, and these are listed on the periodic table. So, as I said, all of the elements are shown on the periodic table, and this groups them together based on their structure and behavior. So what we can see here is the periodic table. I'm sure you're all familiar with it and have seen it before. And it really is a really impressive feat of human ingenuity, really. And I would recommend that you go online, and if you search for an interactive periodic table, you can actually go through all of the different elements on it and learn a little bit about maybe not all of them, but you can certainly look at some of the ones that are of most interest to you and to us. So the ones that we tend to discuss in biochemistry and in biology quite a lot, you can see some over here. So there's carbon, which we'll talk about in a bit more detail in a minute. Nitrogen, oxygen. Up here to the top left-hand corner, we have hydrogen. You have these sort of very reactive metals, so lithium and sodium and potassium. Sodium and potassium we'll see quite a bit over the coming lessons. They're very important in biology. So it's a very interesting thing, the periodic table, and it's all put together in various groups and periods, hence the name. So if you're interested in chemistry, then by all means have a look at it. Okay. So back to this then. So out of the 92 naturally occurring elements then, only about 25 or about 20 to 25% of those are essential to life. And particularly for humans, we're made up of 25. So those are the elements that are essential to life. So we're actually fairly simple. Different species across the different kingdoms of life will be made up of slightly different elements, but most of us are between 20 to 25%. For us, out of the 25 elements that actually make us up, we're only made up of mostly 4 of them. So about 96 to 98% of us is made up of just carbon, oxygen, hydrogen, and nitrogen. And out of that, actually oxygen is by far and away the most common, being sort of about, you can see down in the diagram there, about 65%. So we're about 65% oxygen, 18% carbon, 10% hydrogen, and about 3% nitrogen. So out of the remaining 2 to 4%, most of it is made up of calcium, phosphorus, potassium, and sulfur. And then we get this a sort of very, very small fraction of a percent, really, that are made up of the trace elements. And trace elements are those elements that are required by an organism, but in minute quantities. So they're essential to life, but we only need them in very, very small quantities. So some classic examples there are things like iron. Iron, I'm sure you're all familiar with, which is an important component of hemoglobin, which enables our blood to carry oxygen around the body. And it's also what gives blood the red coloration. Iodine is another one. It's really important to the thyroid gland, so it's very important in helping to regulate metabolism, mood, and energy levels. And different species will have different trace elements, and they will have different amounts of these that they need. So depending on what animals you're keeping, or what plants you're keeping, or what fungi you're keeping, it depends on sort of what you decide to keep or what you end up working with. Each species, or all different species, will have different trace elements that they require in specific amounts. And with a bit of research, you can usually find this out fairly easily. So as an example, one of my main interests is aquatics. So that's keeping corals and keeping fish and plants in freshwater tanks, but corals in marine tanks. And the corals and freshwater plants, they require trace elements, but they require them in different amounts. So it's important that I do a little bit of research and I make sure that I'm providing the right trace elements at the right times and in the right amounts. Because like a lot of things, more isn't always better. Like anything, too much of something can be toxic. So again, these things are necessary, but make sure you do a bit of research and provide them in the right amounts. But to summarize that slide then, most life is made up about 20 to 25% of the 92 naturally occurring elements. Humans are made up of 25 of those elements. Mostly we are carbon, oxygen, hydrogen, and nitrogen. The remaining is calcium, phosphorus, potassium, and sulfur. And then we also get a small amount of trace elements as well. So when we look at the periodic table, what we see is a bit of information on there. When you look at an individual element on the periodic table, you're not sort of overburdened with information, but the information on there is really important, and it tells us an awful lot about the atoms of those elements. So as we can see there, an element's properties depend on the structure of its atoms. So each element consists of unique atoms, and an atom is the smallest unit of matter that still retains the properties of an element. So I've got a picture there of the periodic table representation for carbon, and essentially you can get down to one atom of carbon, and that is the smallest unit of matter that you can get to while still retaining the properties of carbon. If you go any smaller than that, then you no longer have carbon, you have a different atom or different element altogether. So what we're going to do next is sort of go through and talk a little bit about why that is. So if we look at that diagram then from the periodic table for carbon, what we can see is we've got basically 4 things that we need to look at. Right in the middle, we have a C, and this is the elemental symbol. And this is typically the first or first two letters of the element name. And it's typically in Latin. Occasionally you'll get it in German. So usually, or quite often, with the elements that we'll be talking about, they will be sort of what you would expect. So carbon is C. But if we go back to the periodic table, what we can actually see is that it's not always the case. So if we look up here, we've got boron, which is B, carbon, which is C, nitrogen, which is N, oxygen, which is O, which is all well and good. And I said that sometimes it's the first two letters. So up here we can see He for helium. But then it's important to be aware that sometimes it's not as you would expect. So if we come over here to the left-hand side, we see that sodium has the symbol Na, and that's Latin for natrium. And if we go just below that, we can see that potassium has the symbol K. So it's not always the case. You always go down to one of my personal favourites here. Down here is lead, which has the symbol Pb, which stands for plumbum. So who said the periodic table doesn't have a sense of humour? So you'll get used to dealing with specific elements, and you'll get used to using and recognising the elemental symbol. But it's just something to be aware of. Okay. So back to the PowerPoint then, back to our carbon. So we've got the elemental symbol, and then just below that we get the element name. So that's nice and straightforward. Above that, and sometimes below it, you'll recognise it as soon as you look at the periodic table, because it's usually a whole number. We get the atomic number, and in carbon's case, the atomic number is 6. And then right at the bottom there, we actually get something called the mass number, or atomic mass. So this diagram isn't the best, actually. It says atomic weight. Physicists and chemists out there would probably not speak to me for putting this diagram on there. So that should really be the atomic mass. So we've got two numbers that we need to be aware of: the atomic number and the mass number. So next we're going to talk a little bit about what those two are. So I'm going to go forward a slide, and then I'll come back to this one again in a sec. So to understand those two numbers, then the atomic number and the mass number, we need to talk first about the actual structure of an atom. And atoms are composed of subatomic particles. And you might be familiar with that term. Subatomic particles have been discussed quite a lot in the news over the last sort of 10 years or so, particularly the search and discovery of the Higgs boson. Scientists have actually discovered about 100 subatomic particles now. So you've got things like quarks and gluons, but that's very much in the realms of physics, and sometimes getting down into quantum physics. And we don't really want anything to do with that. Unless you're interested in it, by all means have a read through and have a look at the literature on it. But as biologists, we don't really need to worry too much about that. We are really only interested in 3 types of subatomic particles. And we'll have a look at those next. So if we look down at the little diagram on this slide, we can see a basic diagram showing a carbon atom. And right in the middle of that diagram, we have something called the nucleus, so the atomic nucleus. And the atomic nucleus is actually made up of 2 different types of subatomic particles. We can see up here, those 2 particles are called neutrons and protons, and they sit together in the middle of the atom to make up the atomic nucleus. Moving around the nucleus, we have our 3rd type of subatomic particle called electrons. And we'll talk more about this as we go through, but in biology, and particularly in the way I discuss it, I like to show and represent electrons as sort of orbiting the nucleus. So it looks a bit like a classic solar system where you've got the sun in the middle as the nucleus, and then the electrons are sort of acting like planets moving around. It's important to just be aware that that is not an accurate representation of how the electrons actually move around the nucleus of an atom. Electrons are far more mysterious than that. So if you were studying chemistry now, you would be sort of learning, and I'd be talking to you about things called orbitals, which chemists tend to use to be a slightly more accurate representation of how electrons move around the nucleus. But you can go even sort of another level down, if you like, or another level closer to it, and start looking at things like wave functions. And you're in the realms of quantum physics and quantum mechanics there, and that is a much more accurate representation of how electrons move around the nucleus. They're not like these little planets. They're much more like a cloud. So they're like a cloud of energy that actually exists around the nucleus. But it doesn't really serve any purpose for us to think about it in that way, because all we want to do is talk about basic atomic structure so we can start making compounds and molecules, so we can get on to talking about animals later on. So anyway, we've got three types of subatomic particles then that make up our atoms. Protons and neutrons form the nucleus, so that's at the center. And then we've got electrons moving around the outside of the nucleus. The next thing that we need to talk about is electrical charge. And these different particles have different electrical charges, and that will become important later on, because it will, particularly with the electrons, it will determine how these atoms interact with each other. So as we can see there on the slide, neutrons in the nucleus do not have an electrical charge. They are electrically neutral, hence the name neutrons. Protons that also sit in the nucleus have a positive charge. So one proton will give us 1 unit of positive charge. Electrons that move around the outside of the nucleus have a negative charge. So 1 electron equals 1 unit of negative charge. And typically an atom will be electrically balanced. So what that means is that there will be the same number of positively charged protons and the same number of negatively charged electrons in that atom. So they sort of the positives and the negatives balance each other out. This does change later on, and we'll talk about that. But typically when you're looking at an atom, or you're talking about atoms, they will be electrically balanced. So if we remember this information, so protons and neutrons in the nucleus, electrons moving around the nucleus, protons are positive, electrons are negative, and neutrons are neutral. We can go back to the previous slide to our periodic table representation of carbon, and we can actually now discuss what those two numbers mean. So first off then, at the top we've got the atomic number. So for carbon, that is 6. And what that number tells us is the number of protons in the nucleus of an atom of carbon. And it's really important to remember that, because the atomic number, which tells us the number of protons, it's an important number, because it is the number of protons that will determine what element you are dealing with. So an atom of carbon will always have 6 protons in the nucleus. And if we go back to the periodic table quickly, let's bring that up. We can see up here, if we look at carbon, it has a atomic number of 6, so you can see the 6 at the top. If it didn't have 6 protons in the nucleus, if instead it had 7 protons in the nucleus, well, if we look to the right here, we can see nitrogen, and nitrogen has an atomic number of 7, which means it has 7 protons. So if this carbon atom had 7 protons, well, it wouldn't be carbon anymore, it would be nitrogen. If it had 5 protons, it would no longer be carbon, it would be boron. If it had 8, it would be oxygen, and so on and so forth. So it's the number of protons in the nucleus of that atom that determines what that atom is an atom of, which element that it is an atom of. The atomic number then tells us the number of protons in the nucleus, and it is the number of protons that determines what element that is an atom of. But if you remember what I said on the last slide, The atomic number, the electrical charge of an atom is typically balanced. So there'll be the same number of protons in the nucleus as there are electrons moving around the nucleus. So when we see carbon and we see it has an atomic number of 6, it tells us that there are 6 protons in the nucleus, but it also tells us that there are 6 electrons moving around the nucleus. So the atomic number will tell us both the number of protons and also the number of electrons. So it's quite handy for that purpose. So moving down to the bottom then, we can see that we've got the mass number, the atomic mass number, and we can see for carbon it is 12.01. It typically is just easier to sort of round those up or down. The reason that they're slightly different, I'll get to in a minute. The mass number tells us the total mass of the nucleus. So it tells us the total number of both protons and neutrons in the nucleus. The easy way of using the mass number to work out the number of neutrons we have in the nucleus is just to subtract the atomic number from the atomic mass. So if we've got an atomic mass of 12 and we've got an atomic number of 6, all we have to do is take 6 from 12, which obviously leaves us with 6. That tells us that we have 6 neutrons in the atomic nucleus of carbon. So the atomic mass gives us the total number of protons and neutrons. The reason that the number is an odd number or a decimal number, you've got a decimal place there, is there's a slight difference in the mass between protons and neutrons. They're very similar, but there is a slight difference. One of the other reasons that there's a slight discrepancy there, or a slight difference, and you've got the decimal place, is that certain atoms or certain elements can have different types of atom. So the number of protons for carbon is always going to be the same, which we established just now. An atom of carbon is always going to have 6 protons, but the number of neutrons can actually differ. So carbon actually exists in 3 different forms. We can get the one that we're looking at on the slide here, which is called carbon-12. Carbon-12 for obvious reasons. It has an atomic mass of 12. But we also get carbon-13, which has an atomic mass of 13. And we also get carbon-14, which has an atomic mass of 14. So hopefully you can work out what the difference is between those 3. And it's just the number of neutrons. So carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 will have 8 neutrons. They all behave chemically in the same way, and that's actually quite useful, because what we can find with carbon-14 in particular is it's an unstable atom. And that means that it's constantly shedding subatomic particles. And that makes it radioactive. That's what we refer to as decay and radioactive decay specifically. And carbon-14 is useful in medicine, so we can use it as radioactive tracers for medical procedures. And it's also used for radiocarbon dating. So you might have heard of archaeologists using that for dating organic material to try and find out how old it is. So it does have its uses. So carbon then comes in 3 forms, and those 3 different forms, based on the different number of neutrons that we get, are called isotopes. So carbon-12, carbon-13 and carbon-14 are all isotopes of carbon. Okay, so we've been through that already. And depending on where you look, you can see the carbon structure, or the elemental structure, the atomic structure of the elements displayed in different ways. So here's just another example of a way that you can look at it. So carbon here, it's a non-metal. This is carbon-12 because it's got 6 neutrons. There's the atomic number of 6. Energy levels I'm going to get onto next. Here we can see the atomic weight, or the atomic mass again. This is information that we don't need to worry too much. The atomic radius. And down here we see something called orbitals. And orbitals is a slightly more accurate way of representing the distribution and movement of electrons around the nucleus. I mentioned it earlier. If you were studying chemistry, we would need to discuss orbitals, but as we're discussing biology, we don't need to. But by all means, have a look at it if you're interested. So, as I mentioned at the beginning, when we look at the world around us, we're not seeing a sort of soup of atoms. We're clearly not a soup of atoms. We have structure to us. There's complexity in the universe around us, from the planets that we see down to living organisms on this planet, maybe other planets in the future, we don't know. So how do we get from atoms to complex life and complex forms that we see around us? Well, we do that by forming bonds between atoms to make compounds and molecules. So we're going to go on and talk a little bit about that next. So a compound is a substance consisting of two or more different elements in a fixed ratio. So we can see some examples of compounds down in the left-hand side of the slide there. So we've got nitrogen oxide, we have water, nitrogen dioxide, carbon dioxide. And the key thing about them all is that they are made up of two different elements. And that's the key to a compound. You've got atoms from two different elements combining. And we'll look at how they're formed in a bit. An important part of a compound, or an important aspect of a compound, is that they will often have very different characteristics to the elements that make them up. So we can look at one of the examples again from the little diagram there. If we take water for an example, if you take oxygen at room temperature, it exists as a gas. If you take hydrogen at room temperature, at normal pressures, it exists as a gas. However, if you combine them in the fixed ratio of 2 to 1, so 2 hydrogens to 1 oxygen, we get water, which is liquid at room temperature and at normal pressures. So we can see that we have very, very different characteristics in the compound than we do from the elements that make it up. And we'll look at another example of that in a second. So the other term that I mentioned just now is molecules. So a molecule is a substance that we get from joining two or more atoms by chemical bonds. So the main difference between a molecule and a compound is that a molecule can be made up of atoms of the same element. So if we look at examples of molecules down on the right hand side there, we can see H2, which is atmospheric hydrogen or molecular hydrogen, which is just two hydrogen atoms joined together. We get the same thing with oxygen, so O2. Most of the oxygen that's in the atmosphere around us exists in this form. We get atmospheric or molecular nitrogen, and the same with chlorine. So a molecule can be made up of two atoms of the same element. But just be aware that a molecule is a word that we do use quite a lot in biology, and sometimes we use it has different meanings. So although we just talked about the fact that water is a compound, we will also say that we can have a molecule of water. So same word, and we just sort of use it interchangeably. So just be aware of that. So going back to compounds, here's another example of a compound having very, very different characteristics to the elements that make it up. So on the left-hand side there, we can see sodium. Sodium is a metal. And then you can join sodium to chlorine, and chlorine is a toxic gas, really horrendous stuff. But if you join them together, sodium and chlorine, in the fixed ratio of 1 to 1, so 1 atom of sodium to 1 atom of chlorine, you get sodium chloride, which is just normal table salt. So you go from two pretty horrendous elements themselves, you join them together in a fixed ratio of 1 to 1, and you get something that isn't just edible and nice on chips, but is actually essential to life. So we need to have a certain amount of salt in our diet, for lots of functions, from our nervous system to maintaining the osmolarity of our blood and our cells. And these are things that we'll talk more about later in the module. But this is a really nice example of compounds having different characteristics to the elements that make it up. So how do we get from atoms to these compounds and molecules then? Well, it's all down to the atomic structure, and in particular the electrons. So we can see here that the chemical behavior of an atom is determined by the distribution of electrons in electron shells. And when I say chemical behavior, I'm talking about how those atoms interact with other atoms, basically how they form bonds and who they prefer to form bonds with. And it's largely down to the electrons. So when we look at the distribution of electrons around the nucleus, we see that they tend to fit into different levels, or what we refer to as shells. And we have these electrons that we refer to as valence electrons, and those are in the outermost shell. And as we'll look at in a moment, electrons are arranged to fit into different shells. And the outer shell is always referred to as the valence shell, and the electrons that fit into that shell are referred to as valence electrons, and it is those valence electrons that will determine the chemical behavior of the atom. I just said valence an awful lot. Okay. So the chemical behavior of an atom is mostly determined by the valence electrons. Now, we do get elements that have atoms with full valence shells. And when this occurs, and I'll show you some examples in a minute, but when we get atoms with full valence shells, they don't need or want to form bonds with any other atoms. So we say that these are chemically inert. So if we go back to the periodic table quickly, let me just find my cursor. Okay, so we go back to the periodic table. There is a group of elements with atoms that have full or complete valence shells, and they're over on the far right hand side of the periodic table. So we can see up here we have helium, neon, argon, krypton, xenon and radon, and these are chemically inert because they have full or complete valence shells. And if you've looked at a periodic table before at school, you'll probably remember that this particular group of elements are referred to quite often as the noble gases. The noble gases, because they sort of stand aloof. They don't want to mix or make bonds with any other atoms. So those elements that have full valence shells then are chemically inert. But what about those atoms with incomplete valence shells then? Well, first we need to talk about something called the octet rule. And this is referring to how electrons are arranged and organized into shells or energy levels around the nucleus. So the octet rule is the tendency of atoms to prefer to have 8 electrons in the valence shell. An important point here is that only 2 electrons will actually fit into the first shell. So I'm going to show you examples of this on the next slide. But as we've already established, when atoms have incomplete valence shells, they will tend to react to form more stable compounds, because not only can the shell fit 8 electrons, it wants to fit 8 electrons, and that is the key. So atoms are always sort of trying to complete their valence shells. So what we have here is a simplified version of the periodic table, just showing us the first 18 the first 18 elements, and it also shows us the distribution of electrons. So we start up here in the top left hand corner then with the simplest of our elements, which is hydrogen. And hydrogen has it's a rare element in the sense that the atoms don't have any neutrons. It's just one proton in the nucleus, and it has one electron moving around that nucleus. But if you remember, I said the first electron shell can actually hold 2 electrons. So we can say that hydrogen atoms are quite unhappy in the sense that they desperately want a complete valence shell. So they desperately want to have 2 electrons in that shell, but they only have 1. So hydrogen will quite happily make bonds with other atoms to try and get hold of that second electron. If we move over to the next atom, or the next element, we have helium. And we can see up here, helium has an atomic number of 2. So that tells us that it has 2 protons in the nucleus. And it also tells us that it has 2 electrons moving around the nucleus. So those 2 electrons of helium will actually fit into that first shell. Remember, the first shell can hold 2, and it can only hold 2 electrons. That's the maximum number it will hold. And therefore, helium is happy. It has a complete valence shell. That is what makes helium part of the noble gases. Helium, unlike hydrogen, will not look to make bonds or interact with other atoms. If we move again to the next one, so we have lithium down here on the left in the middle. It has an atomic number of 3, so 3 protons, 3 electrons. So we can look at how those electrons are distributed. Well, 2 electrons will go into the first shell. So we know that it will hold 2 electrons, so that's great. But that leaves us with a third electron. It won't fit into that first shell, so it has no choice but to move out a level, and it moves into the second shell. So if you remember from the previous slide, I talked about the octet rule. And the octet rule tells us that atoms will like to have 2 electrons in the first shell, but then 8 electrons in the subsequent shells. So lithium only has 1 valence electron, but it can hold 8. So lithium is a deeply troubled atom, or the atoms of lithium are deeply troubled. They only have 1 valence electron. They want 8 in that second shell. So lithium is highly reactive. It will look to either get rid of that spare electron or try to find 7 more, which is obviously quite a task. And as we move along that second row, we can see that as we move up in atomic number, so we keep adding protons to the nucleus, we're also adding electrons. So we have beryllium there with 4, boron with 5. Here's carbon that we looked at earlier on. Carbon with its atomic number of 6. So we know that it has 6 protons in the nucleus and then 6 electrons. So 2 go into the first shell and then 4 go into the second shell. And like as I was just discussing with lithium, carbon can fit 8 electrons into that second shell, into its valence shell. Not only can it fit 8 electrons, it desperately wants to fit 8 electrons. That means that carbon can actually make bonds with 4 other atoms because there's space for 4 more electrons in its valence shell. And that might seem inconsequential, it might not seem that important, but it really is. Because carbon can make 4 bonds with 4 different atoms, it means that carbon can make really big molecules, really big compounds. And that is why carbon is the basis for life as we know it. All life that we are aware of on this planet is carbon-based. And it's carbon-based because it has these 4 valence electrons, allowing it to make 4 bonds with 4 other atoms. And there are some scientists that hypothesize that if we find life on other planets at some point, which hopefully we will, it may be silicon-based. So if we move down one, we can look at the element silicon, and we can see that it has an atomic number of 14. So 14 protons, 14 electrons. So 14 protons in the nucleus and then 14 electrons moving around it. 2 electrons go in the first shell, 8 go in the second shell, but that still leaves us with 4. So 4 will have to move out into a third shell. But that also means that silicon can make 4 bonds with 4 other atoms. So it's hypothesized that we may find at some point life that is silicon based. We haven't, as far as I'm aware at the moment, but it is hypothesized that it is possible, or theoretically possible. And then we can sort of move around. If we complete our second row here, we can see the second of our noble gases, neon, which has an atomic number of 10. So 10 protons in the nucleus and 10 electrons moving around it. So 2 electrons go in the first shell. That leaves us with 8. And those 8 electrons fit nicely into the second shell, which completes the valence shell for neon. So neon is one of the noble gases. It has a complete valence shell. It has no interest in making bonds or mixing with other atoms. If we move down to the first of our third shell elements here with sodium, well, sodium has 11 protons in its nucleus and then 11 electrons, so 2 in the first shell, 8 in the second shell, and that leaves 1 more that goes in the third shell. And again, this makes sodium a very reactive element because it has just that 1 electron in its valence shell. And then we can sort of move along. We've got magnesium on 12, aluminium on 13, silicon at 14, phosphorus at 15, sulfur at 16, and then we have chlorine over here with 17. So chlorine, atomic number of 17, 17 protons in the nucleus, 17 electrons moving around the nucleus, 2 in the first shell, 8 in the second shell, and then 7 in the third shell. So that means that chlorine needs to get hold of 1 more electron to complete its valence shell. So keep that in mind. It will become important in the next video where we start looking at chemical bonds. I'll just finish off there. We can look at argon there, which is the third of our noble gases. So argon with its atomic number of 18, so 18 protons, 18 electrons, 2 in the first shell, 8 in the second, and then 8 in the third. So although argon has 3 electron shells, its valence shell, its outer shell, is complete according to the octet rule. So argon, again, is a noble gas. It does not want to mix with other atoms. This is a table that just shows the same information that we just looked at, just in a different format. So we can see here the electron arrangement for the first 20 elements. We have the element name followed by the element symbol, and then we can see electron shells 1, 2, 3, and 4, and we can see how many electrons fit into each of those shells. So hydrogen up here just has the 1 electron, which fits in the first shell. If we come back down all the way down here to carbon, we can see that carbon, we know, has 6 electrons, so it has 2 in the first shell and then 4 in the second. If we come down to sodium that we looked at on the previous diagram, it has 11 electrons, so 2 in the first shell, 8 in the second, and then 1 in the third. So you can use that table as a nice, easy way of looking at the electron distribution for the first 20 elements. So we now know about atomic structure, about the three subatomic particles that make up our elements, the protons and neutrons in the nucleus, the electrons that move around the nucleus, and we know that the electron distribution is what determines the chemical behavior of the atoms of our elements, in particular the valence electrons. So those valence electrons are those electrons in the outermost shell, or the valence shell. So what we're going to do next is, or in the next video, is talk more about chemical bonding. So just to sort of lead up to that then, atoms within complete valence shells can share or transfer valence electrons with certain other atoms. So we've got 2 main types of bond that we're going to look at in the next lesson or in the next video. And that is this sharing and transferring of valence electrons. Once this occurs, so once we get the sharing or transferring of valence electrons, it results in atoms staying close together. And they stay close together because they are attracted to each other. And these attractions between the atoms are called chemical bonds. The two main ones that we're going to talk about in the next video are ionic and covalent bonds. Okay, so let's just do a quick recap then. So there's 4 questions here. I'd like you to pause the video and have a go at answering those 4 questions. And so pause the video, have a go answering the questions, and then when you're ready, resume the video and I will go through the answers with you. Okay, so welcome back. Hopefully you've had a chance to answer those questions. So let's go through them. Number 1, how many elements are essential for human life? Well, the answer is 25. But if you wanted to go a little bit further, you could also have said that we are mostly carbon, oxygen, nitrogen, and hydrogen, but we're made up of 25 different elements. Number 2, what 3 subatomic particles make up atoms and what are their electrical charges? So we've got protons, which are positively charged, electrons, which are negatively charged, and neutrons that have no charge, so they're electrically neutral. Moving on to number 3, what are valence electrons? Well, valence electrons are electrons in the outer shell of an atom. Obviously, we also call that outer shell the valence shell. And it is these electrons that will determine the chemical behavior of an atom. And then number 4, what tends to happen with atoms with incomplete valence shells? Well, they will typically share or transfer electrons with other atoms, creating chemical bonds. Okay. So that brings us to the end of this video then, where we've just done hopefully a gentle introduction to elements and atoms. We've looked at the basic atomic structure, and we've talked about the difference between compounds and molecules. So once you've sort of digested this information a little bit, you can move on to the next video where we're going to be looking at ionic and covalent bonds. Okay, thanks very much.